The statement of Ehrenfest is this theorem states that the average motion of a wave packet agreed with the motion of the corresponding classical particles. Newton's second law of motion may be derived from Schrödinger time-dependent wave equation. This is given as I h cross del psi by del t is equal to minus h cross square upon 2m del square psi plus v psi is equal to 1. Psi is wave function, eigenwave function, mass m is, and this derivative of this wave function, del operator, this v is potential. The particle is under potential v. If v is equal to 0, so potential will be 0 and that particle is in free state. So this one is I h cross del psi by del t. I h cross del psi by del t is equal to minus, if we take the common, h cross square 2im. H cross square 2im. Then this value will be del square psi minus 2m h cross v psi. This is equation 2. But in this case, we have to operate here IH cross. The complex conjugate of the wave equation del psi star upon psi is equal to h cross square 2im del square psi star minus 2m h cross square v psi star, and this one is equation 3. This one is equation 3. So in this way we have taken first पहला जो इक्वेशन है श्रोडिंगर टाइम डिपेंडेंट इक्वेशन है, इसको थोड़ा सा हमने ट्रांसफर किया डेल साई बाई डेल टी के फॉर्म में, एंड दिस इज नथिंग बट माइनस एच स्क्वायर 2im del square, this is del square psi minus 2mh square. Since here it is h square, then we can modify it as psi, in this case as it is, because h is here. So this function is minus h upon 2im del square psi minus 2mh cross square v psi, and complex conjugate, that is psi star. So del psi star upon del t is equal to h cross 2im. This is the I, 2im del square psi star minus 2m h cross v psi star. This is equation number 3. So we have these three equations, that is equation 1, 2, and 3. Equation 1 is the very basic equation, and equation 2 is the transform equation of the first, and equation 3 is the complex conjugate of this equation. Now the expectation value. The expectation value of x. X is position. Position can be expressed as this is minus infinity to plus infinity psi star x psi, and this is d gamma in the three-dimensional space. So what we find the meaning is something like this. One is the line, here it is plus infinity and this is minus infinity. So from minus infinity to plus infinity, there is a x in the value, then we can integrate, and then that integration is position, somewhere exists in the space. Now take the time derivative of position, time derivative position x. We have d of dt of x is equal to d of dt. This is psi star x psi d gamma. So if we take the derivative, that is, then there are two functions, that is complex conjugate of psi and this way. So what we find, d psi star by dt x psi d gamma plus psi star x d psi by dt d gamma inside the derivative. Now what we have to do, substituting this value of psi d psi star dt, and here it is d psi by dt from equation 2 and 3. Substituting the values of d psi star by dt and d psi by dt from equations 3 and 2 respectively. That is, there is a position x and derivative. So this is the value h cross upon 2im del square psi minus 2m h cross v psi star x psi d plus the first term is here over and this is closed. The second term, that is integral of psi star x, and then this is the minus h cross upon 2im del square psi minus, here it is plus 2m h cross square v psi d gamma. This. So what we find in this case, we have just two terms, this 2m h cross v psi x d psi, and here it is plus 2m h cross v psi and psi star x. So these two terms are cancelled out. These two terms are cancelled out. So if we cancel, then simplified equation is d of dt of x is equal to, there is an integration of h cross 2im del square psi star into x psi d gamma, the first part, plus the second part is psi star x minus h upon 2im del square psi d gamma, del square psi d gamma. So this one is equation 4, expectation value, and substituting its value, that is equation number 5, and here simplified equation from this is equation number 6. Equation number 6. From this equation 6, the first integral can be integrated by parts as integral over volume, because there is a d gamma square psi star x psi d gamma is, this is volume converted into the surface of xi into, this is psi star, the differential integrated, and this is d gamma minus dv del psi star into del, this is xi d gamma. So is this factor, surface factor, is 0 due to psi vanishes at a great distance. 0 due to psi vanishes at the great distance. Great distance. What do you mean by great distance? Suppose this is the wave packet. This is the wave packet. So the existence of this wave packet is very finite. In this infinitely large position, this value will be decreased. So the value is minus del V. This is psi star, and this is del xi d gamma. Xi d gamma. Now again, if we integrate it by integral by part, then we find this is again surface, and here it is psi star, and this is del square xi d sigma minus volume, this is psi star del square xi d gamma. Again, this part is 0 at the same region as it was mentioned earlier. So this value is this minus and this minus plus. This is V psi star del square xi d gamma. So what do we find? We find this is left-hand side. This is integral over volume psi star x d psi d gamma is equal to this value. And this equation is equation number 7. So from equation number 6 and 7, from equations 6 and 7, we have what we have. This is d of dt of this x is h cross upon 2im. This is volume psi star del square xi d gamma minus h cross 2im psi star x del square psi del gamma. This is equation number 8. So we have d of dx dt of this x. This x is equal to h upon 2im if we take it common. So what we find, this is psi star del square xi minus x del square psi d gamma. And this is h cross upon 2im and this value, that is del square x psi minus x del square psi, this value can be simplified as, inside the bracket, this is del of del x psi minus x del square psi, that is del x psi plus x del psi minus x del square psi. This is del square x psi. This is del square x psi plus del x del psi plus del x del psi plus x del square psi minus x del square psi. So these terms cancel. These terms cancel. Del square x psi plus, this is del x psi, del x del psi. So it is 2 del x del psi. Now here it is del square psi. Del square psi is 0 because del x is constant. And del square x is del of constant. And del of constant is 0. And that's why it is 0. So this value is 2 del x into del psi. So substituting this value, that is, this is psi star, here it is 2 del x into del psi d gamma. So this 2 cancel. This 2 cancel. So what we have, h cross im, this is integral psi star del x into del psi d gamma. So what we have, if you see, this one is del psi, it is a constant quantity. This is the constant. So h cross im psi star del psi d gamma. So this is nothing but, if I take, this is 1 upon m mass, then it is psi star h cross over I del psi d gamma. This is 1 upon m, this is psi star, and this value is I. If we multiply both sides, that is, if we have h cross over I, then this is I h cross over I square, and this I square over is equal to -1. So this is minus I h cross. So this h cross over I is equal to minus I h cross, and this is del of del x psi d gamma. And from the previous notes, this is nothing but, it is the expectation value of the, this is the expectation value of the position, momentum. So where this is momentum operator psi star p psi d gamma, and this p is equal to minus I h cross del of del x. This p is equal to minus I h cross del of del x. Yes. So what we find this is the rate of change of position. This is d of dx of x, that is position. This position, rate of change of position 1 upon m expectation by value of p. P is mass into velocity. So P is, if you are substituting, P is equal to mass into velocity. So mass cancel. So there is a V. And this d of dt of x is equal to V. So a rate of change of expectation value are the 1 upon m into expectation value of P. So this is part 1. This is part 1. This is the first part of the statement. Now the second part of the statement is as we say, force is equal to rate of change of momentum. Force is equal to rate of change of momentum, and this is del V by del X, rate of change of potential, energy, potential. So for this, we can say the expression for the expectation value of the momentum, can be expressed as d of dt of p, that is rate of change of momentum, which is force. So the rate of change of expectation value of momentum is defined as d of dt, and this is psi star p psi d gum, and this is nothing but d of dt. This is what it is, minus infinity to plus infinity. It is minus infinity to plus infinity always. Then it is psi star, and the momentum operator is this value, this psi of d gamma. Say this is the equation number 10. This is the equation number 10. So this value is IH cross. If we take this value is IH cross outside. So what we find, this is integral of psi star del of del x into d psi by dt of d gamma plus integral of d psi star by dt plus d psi by star dt plus this is multiply d psi by dx into d gamma. This one is. So if we substitute again the values, which values, that is from complex psi star d of dx, and here it is IH cross del psi by del t d gamma. This is plus, here it is minus IH cross del psi star by del t into del psi del x d gamma. So these two expressions are from the Schrodinger time dependent equation, and its value can be substituted from Schrodinger time dependent value. The if we substitute this value, then this is psi star d of dx. Psi star d of dx is equal to minus h cross square upon 2m. This is del square psi plus v psi d gamma plus. This is integral. This is the integral inside the bracket minus h cross upon 2m del square psi star plus v psi star and del psi by del x d psi. We are just substituting the time derivative of the Schrodinger equation in time dependent form. So if we take this common, h cross square 2m, then the value is psi star del of del x, and here it is del square psi. This is del square psi. And from this case, del square psi star. So minus del square psi star into del psi by del x d psi minus this is psi star del of del x v psi minus v del psi by del x d psi del psi by del x d psi. So if we group these equations, that is, now we can again integrate the equation by parts and discard the surface integral because it will vanish. It will vanish at infinitely large distance. Infinitely large distance. So we have this is del square psi star del psi by del x d of this is minus del psi star del of del x psi d gamma is equal to psi star del of del x psi square this gamma. This is equation number 12. So what we find by discarding the surface integral part, that is first of the integral will be 0, and this part is here. So what we find, therefore, we have the final equation as d of dt of p is equal to minus psi star del v by del x psi del v by del x psi d psi. So this is psi star minus, we take this minus del v by del x psi d. So this can be expressed as expectation value of minus del v by del x. Expectation value of minus del v by del x. So d of dt of this p, that is force, this is nothing but force, is expressed in terms of the force. This is the force. So these 12, here it is 13. So these two equations that is equation 9 and equation 13 are analogous to the classical equation of motion. Analogous to the classical equation of motion as velocity and force. As velocity and force. So from the first discussion, that is, we have given the concept of position and its expectation value, that is x, and then rate of change of position d by dt of expectation value of x is nothing but it is velocity, and that velocity is here quantum to classical. That velocity, this equation is that velocity is nothing but this is the p over m, because we know p is equal to mass into velocity. So if m is there, mass cancel, and the remaining part is velocity. And similarly, the second equation, force F is equal to rate of change of momentum, and this is minus del V over del rate of spacing, the space rates of potential change from one place to other place. Here it is the V potential, here the V2 potential, there is a change of height, then that will give the force. So the rate of change of momentum, that is force, is expressed in these terms. That was also achieved in this Ehrenfest theorem. By assuming the several waves superimposed to form wave packet, and that wave packet is nothing but it is the wave particle. So what do we find? Finally, we find that there is a principle of correspondence. This is the principle of, this is the correspondence. Principle of correspondence. Which principle? It is Bohr's. It is Bohr's correspondence principle. Now, which states that in approximate limit, the quantum computation reduced to the classical calculation. The quantum computation reduced to classical computation. And I like to add one more thing, that the coming science, advanced science, that is when we talk about quantum computer, then quantum gate, qubit is converted into the beat, that is the classical beat. So this is all about the today lecture. About this one is, now this session is open for discussion. यदि आपको कोई प्रॉब्लम है तो you may ask the question.